again. I'm Michael, that's Sam, and that's Brock.
Yep. Alright, so apparently we didn't get across the concepts of existential graphs very well the first time, so we're going to try that again. The basic part of existential graphs is this thing called the plane of truth. Everything on the plane is true and conjuncted together. So this means implicitly P and Q. There's also one operand in existential graph, and only one operand, and that's a cut. And anything in a cut, which is represented by this circle type thing there, is negated. So this canvas represents not P. And existential graphs is a complete logical proof system, so we can represent anything that we want to in existential graphs. This particular thing represents not P's or this represents literally not P and not Q, which is logically equivalent to P or Q. There's 4 rules in existential graphs for doing proofs. The first one is double cut. You can add a double cut around any group of variables or cuts or anything like that, or you can take it away, which is indicated by the 2-directional arrow on the screen there. The other bi-directional rule is iteration and de-iteration. So you can at any time copy something that is in a higher level into a lower level. Well, whatever you want to call it. Into a subcut. Or you can duplicate something within the same level of the cut. So you could add a second A up here if you wanted to then move on to double cut it or something like that. The third rule is deletion. You can only delete stuff on even levels. So you can delete stuff on the raw canvas, but that would be kind of hard to show. And you can also delete stuff on this second level down, and now there's nothing there anymore. And the final rule is insertion. You can add whatever you want on odd levels. So there's blank, and there you have an A.
How does that second example make any logical sense if you're going from A to A and not A, which is a contradiction?
Well, no, that's just an example of how it works.
Iteration, de-iteration.
That's like the one that's the hardest to explain in general senses. You're actually going from like not A to sort of not A or A. So this is actually, when you think about it, it's A or not A, which makes complete sense. So it's like I find like these the other 3 rules besides iteration and de-iteration map really well with other like logical functions that we have. So this one's sort of the outlier. It works though, so trust us on this.
Because this is an empty cut, which means not. So basically this is false and A, which is a stronger statement than not A and A. So they're both contradictions, but
They're both
yeah, they're both tautologies.
Because that's true.
That's cut it.
oh, right.
Anyway,
Same general idea.
any other questions on that?
It's kind of a source change.
Yeah. So
Anyway, as I was saying, this is an example proof. So the first step of the proof, starting from a blank canvas, is a double cut. And then from the double cut, we can move on to insertion. So we're adding something on an odd level. Then we're doing iteration. So we're moving this in here. And finally, we're doing another double cut. And this, in the end, proves A or not A, which is a tautology. And now it's his turn.
Oh, did I get a mouse?
Yes.
yeah.
Ooh, okay. So, what do we have working so far? So we have cuts and variables. And we have 3 out of the 4 inference rules. And like Mike said, iteration and de-iteration is the hardest one. And he'll be talking about that. But other than that, we have them mostly working. And we have a better interface and fancy stuff using Raphael.js, like zooming, context menus, and collision detecting. And we have a working proof system, so you can actually go through a proof back and forth and see a demo.
There you go. So what do you want to do?
Okay. So this is what our interface looks like. You can double click and you can insert stuff, so you can insert cut, pull out another cut around it, move it around.
So right now we don't have insertion implemented in the front end. So
There's weak insertion.
yeah, you're allowed to do insertion. So that's why you could just put in cuts and stuff. In the end, we're going to separate it into two different modes. One for creating the premises, and then it's going to restrict you to just using the inference rules after.
And then, so we did a couple rules, right? So you can go back, see the rules that you did, and then go forward. You have like an undo redo stack. That was actually complex because you have to like compress a tree and then do some fun serialization type stuff. Also put in variables. So hello, variable, and you can perform the rules on that too. And then take away a double cut, which is the opposite. So it's basically the system we have working right now. Go back.
Yeah.
I don't know how to use this magic machine. Okay. And what do we have left to do? Well, we have iteration and de-iteration. A better version of insertion, because the way insertion is supposed to work is you can insert anything, but that means you have to make the proof pause in a sense, so you can insert anything you want on the level. And then have a way of going from premise mode to proof mode, which we're acting as the same thing right now. Multi-selection for things, some GUI updates, saving and loading, and hopefully multi-touch input for tablets.
Okay, so I'm actually going to talk about an interesting problem that came up in sort of a few of the rules and a few extra things that we might want to do in the end. And it's somewhat related to how we sort them. So we sort in a pretty natural way, actually. It's just a tree. And it's not a specific tree, but it's a tree that basically easily gets the entire structure of this frame of the proof we're currently working on. You just have the root be the plane, and then any child is either going to be a variable, which means it's on that plane, or it's going to be just a node, which symbolizes a type. So that's how we store it. It's pretty easy to transition between the two, but it's really good for computers. Now the problem is, what we wanted to do was be able to say if a subset or even the whole tree was the same as another part of a different tree. And that's known as tree isomorphism. And normally this is actually a pretty simple problem, it's linear, but ours got a little bit more complicated because of the variables. So instead of just trying to match up the structure of the tree, we're also trying to match it up so that the structure matches and the variables match in the right place. While this might not sound like it's too much extra work, it gets a little bit more complicated because if you had, say, like a highly symmetric, like a complete binary tree, and then at the end you just had all these different variables, there could be a huge amount of ways that you could have matched those trees that would be a correct structural matching, but maybe only one or maybe none would have actually been a correct matching with the variables included. So that sort of check, if you were going to brute force this, would quite obviously be close to exponential, if not higher. So that was our problem. It actually comes in, probably the most obvious case would be de-iteration. You have to check that before you can remove something. You have to check that it's the same here and here, on the inside and on the outside. And other potential uses would be things like, in the end, if you want to prove a goal, maybe, entering your goal in first, and then sort of being able to progress towards it. So we actually had a few different ideas of how to solve this. The most obvious one that came out like first was to try to sort the tree. But it's sort of complicated sorting the tree and not very efficient. That you have to do it like every time you do it, and I was guessing it would be like an n squared operation or something. I also then semi-recently came up with an idea that was like n to the fourth, which was combining dynamic programming and bipartite matching. So craziness. But Broth actually suggested something using gadgets, which is what we're trying to go with right now. And this is what it is. So the first thing we do, and we're going to sort of go through it, is we go through all the trees and we just take a list of all the variables that are used. Obviously, we do some checks to make sure the same variables are used in each tree, yada, yada, yada. But once we have that list of variables, we assign each variable a number starting from 2. So in this, our example, we're not going to actually compare two things. But so that would be what the graph would look like to the user. That's how it's represented. And as you see, since there's only P and Q, so we're going to assign a number, so we're going to assign 2 and 3. Why we don't use 1 is going to come in later, but
Next slide.
yeah, next slide. So really what gets the identity of 1 is the empty node. So if there's nothing there, we need to represent that, because what we're really going to do in the end is we're going to modify this tree so that the structure represents the variables that are in it. So if there's an empty cut, what we do is we give it child, and then we give it 1 child, so an ID of 1. Then for each node that has a variable, we replace that variable with a node, and then that many children as its identifiers. So what you get after this is that the leaf node, or all the leaf nodes are sort of like ID nodes that represent what type of variable or empty cut is at that bottom level. And you get a node at the one level up that sort of just separates everything. And if you take that, you just run a normal tree isomorphism algorithm, you should get the result you're looking for. And that should be about like an n squared algorithm instead of something ridiculous like n to the fourth or exponential. So that was pretty good, we thought. So, any questions?
The last line, can you explain the third leaf? Where do you have 2?
Okay, so right here, this got a little bit confusing because of the weird coloring here. This node and that node are the same.
Okay.
So weird coloring, forgive us.
Okay, that's
But that's just saying we're replacing this with that. Yeah?
Is this all in JavaScript or is this server?
We're programming this in JavaScript, and we have a little bit of HTML, yada, yada,
Yes,
yada.
we're eventually taking it to a server-side type. Who asked the question? Yeah, so we're eventually taking it to a server-side type thing because we want multiple users to be able to work on a proof because this is going to be used in a teaching environment.
Sure.
It's going to have like the teacher say, oh, here's proof, and put the students solve it.
You might look at the node for that, since
Yeah.
you probably won't need to change a lot of stuff.
Yeah, that's what node's always fun. Yeah. Anything else? Ah,
Well, yeah, I'm wondering, I don't know what the normal tree isomorphism algorithm is, but is the idea behind it applicable immediately to the original graph without replacing stuff?
Well, the idea is just for like a general tree. So that's just a graph, not having any variables or any special things. So all it does is it compares the structure of 2 separate graphs and says, are they structurally equivalent? When you get into the variables, it makes it so the structural equivalence isn't enough for your problem. This sort of modification with a few gadgets here
it just makes the
actually
nodes
makes it
worse.
so that the structural equivalence also includes the variable equivalence, which allows it to do the correct stuff. Yeah.
What's the running time of graph quality?
General, general might be, well, I don't think generalized.
I really just don't get why you can't do it linearly.
Well, this okay.
Graph isomorphism is very hard.
Very hard. I don't think it's empty.
Yeah, this tree, in fact, I posted a comment in your blog about this problem prevented unification.
Yeah.
So I didn't hear back. So that
Yeah, well, I actually just was looking at that.
Okay.
I think the difference between this and unification is that this isn't like a sorted structure. So it could be arranged differently.
Okay, so that arguments.
So the arguments aren't necessarily in the same idea, which makes it more complicated. If you had a general tree, though, yes, it is a linear operation to compare if two trees are isomorphic. The fact that this is n squared is just because we're adding a potential factor n when we modify the
Worst
tree.
case n squared. Average case it's still around n.
Yeah. Yeah?
Is there like a lag? Is that why you try to improve it, or is there?
Well, I think a lot of the idea behind this was just it was an interesting problem, and all of us are pretty good at algorithms. We just wanted to make an efficient solution for it.
Okay.
So, probably in most user cases, it wouldn't make too big of a difference even if we just brute forced it.
I still don't get it. What is it about the isomorphism algorithm that can't translate to, right? Why can't you kind of tweak
Because
that?
in isomorphism, the nodes are ambiguous, so all the vertexes.
It assumes that everything could be anything.
Yeah.
So if I had like a tree with two children, it assumes that if it assigned one matched one child to one node and the other child to a different node, that would be the same as the reverse of matching it the other way. So when you have the variables, you can't make that assumption because you might be matching A to B and B to A.
One way of understanding this is chemicals. If you think of chemical structures, like when you have a chemical structure, there is some associated with each node. You have either a carbon or a hydrogen and so on. So the node has some property associated with it. Similarly, you have something associated with that. That is why just isomorphism. That's what it is.
Is isomorphism NP hard?
No, that's an open
It's not.
question.
I'm pretty
It
sure
is an open question.
Open
whether
question,
it is-
yeah.
whether
It
is-
hasn't been proven.
Yeah.
I know that much at least. But it's a hard problem if you aren't using like a tree, which is pretty special. So, any other questions? Yeah?
So as far as storing the data is concerned, because right now you have sort of a couple models of how to store a proof or a premise or what have you. One of which is you can have it just as a tree with nodes with no data in them like this, and you have it one way, and the other is to have it with sort of an identifier with a name and that sort of thing. Are you going to save it as a tree with identifiers and then translate it to this whenever you need to run this algorithm?
Yeah, the current plan is to translate it every time we run the algorithm because
It's just a reduction.
yeah, it's the IDs we're sort of giving it wouldn't be used anywhere else, and when we're inserting and removing different variables, if we kept a record of that, then potentially if you were going to be really what's the word, like an enemy of the system, you could just keep creating and removing variables, and that would make this take forever, because if you have a node that has an ID of like 1 million, then it makes the isomorphism take that much longer. So, any other questions? Yeah?
So when can I use this?
Well, right now we've got most of the stuff implemented in the backend minus iteration deiteration. We're getting the front end sort of working. So you can, in theory, do some simple things right now, but we're planning on having a working version by the end of the semester.
More importantly, when can I use this and my students in electric course?
Well, hopefully as soon as we get it working.
Yeah. It's more mid-summerish because there's some extra stuff we need
Well,
to add.
there's a whole ton of extra things you can add,
Yeah.
but just the
So you
simple
have to check it.
proving should be done by the end of the semester. Okay. Well, thank you, everybody.